Good afternoon everyone. Myself Harpreet Kaur from GPCG Jalandhar. Today my subject is microcontroller and embedded systems and my topic is interfacing of microcontroller 8051. In this topic we will cover the introduction of interfacing, then interfacing of LCD with 8051. Interfacing the keyboard to 8051 microcontroller. After that interfacing of 7 segment displays, then interfacing of A to D converter with 8051 and then interfacing of digital to analog converter with 8051. At the last interfacing of sensor with 8051. Now, introduction to interfacing. Microcontrollers are used as the brain to control a large variety of products. In order to control devices, it is necessary to interface or connect. Interface means to connect them to the microcontroller. For input interface, keyboard, limit switch, A to D converter, etc. can be used. For output interface, 7 segment display LCD, that is liquid crystal display, DAC, that is digital to analog converter, relays, transistor drivers, etc. can be used. Interfacing of LCD with 8051. LCD advantages. In recent years, the liquid crystal display is finding widespread use, replacing LEDs. This is done due to the following reasons. Number 1, the declining prices of LCD. Second point, the ability to display numbers, characters and graphics. The age of programming for characters and graphics. Liquid crystal display is a cheap and easy way to display text. LCDs are available in various configurations. Integrated controller. They have integrated controller. The display has 2 registers. One is command register, other is data register. We can select any one of these registers by RS pin. By making RS pin 0, we can select command register, and by making RS pin 1, we can select data register. Data lines, that is DB0 to DB7, used to transfer data and commands between LCD and microcontroller. To display any character on LCD, microcontroller has to send its American Standard Code for Information Interchange value to the data bus of LCD. For example, to display AB, alphabets AB, microcontroller has to send 2 hex bytes, 41 in hexadecimal and 42 in hexadecimal respectively. For A, we have to send 41 in hexadecimal, for B, we have to send 42. Now, we have LCD pin descriptions. In LCD, we have 14 pins. First pin is VSS. VSS is connected to ground. Then we have second pin, that is VCC. It is connected to positive 5 volt power supply. Next, we have VEE. This is connected to variable power supply to control the contrast. Next, we have RS pin. This is input pin for the LCD, and when we make RS equals to 0, it selects command register. When we make RS equals to 1, then it selects data register. Next we have another input pin, that is read write. When read write pin is 0, it is used for write. When it is 1, then it is for read. Next, enable pin. Enable pin, it is used to enable the 8-bit data to LCD pins. This pin is made from high to low. Then we have data bus, that is DB0 to DB7. We have 8 pins for data bus. This is bidirectional data bus. Next we have LCD command codes. There are also instruction command codes that can be sent to LCD to clear display or force the cursor to home position or blink the cursor. Next, here the LCD command codes are given in hexadecimal number system, and this is the description for that hex code. For 1, clear display screen. Then for 2, return home. For 4, in hexadecimal, decrement cursor and shift cursor to left. 6th, increment cursor and shift cursor to right. Then 5, hexadecimal. In hexadecimal used to shift the display right. 7 is used to shift the display left. Then 8 is used to display off, cursor off. A in hexadecimal used to display off, cursor on. Then C is used display on, cursor off. E in hexadecimal is used to display on, cursor blinking. F in hexadecimal is used to display on, cursor blinking. Next 10, shift cursor position to left. 14, in hexadecimal is used to shift cursor position to right. 18 in hexadecimal is used to shift the entire display to left. Then 1C in hexadecimal is used to shift the entire display to right. 80 in hexadecimal is used to force the cursor to beginning of first line. Next, C0 in hexadecimal is used to force the cursor to the beginning of second line. 38 in hexadecimal is used for 2 lines and 5:7 matrix. This is the interfacing, that is LCD connection of LCD with 8051. Here 8051's 2 ports are used. Port 1 is connected with bidirectional data bus, and the port 2 3 pins are used and they are connected. Port 2.0 pin is connected to RS, that is register select. When this is 0, RS is 0, then command register is selected. When RS is 1, then data register is selected. P2.1 for write. To write something on LCD, we make this pin 0, and to read we make this pin 1. Then we have enable pin. Enable pin is used, is input output pin. When data is supplied to data pins, a high to low pulse must be applied to this pin in order to latch in data present at the data pins, minimum for 450 nanoseconds. Next, sending commands and data to LCDs with a time delay. To send any of the commands to LCD, make pin RS equals to 0. That is, it selects command register. For data, make RS equals to 1. Then send a high to low pulse to enable pin to internal latch of LCD. Now we have program for interfacing LCD. Calls a time delay before sending next data or command. Pin number port 1.0 to P1.7 are connected to LCD data pins D0 to D7. Pin number of port 2 P2.0 is connected to RS register select pin of LCD. P2.1 is connected to read write pin of LCD. Then P2.2 is connected to enable pin of LCD. Now program. First of all, this is a directive, that is origin. Origin of the program is at 00H. Then move 38H to accumulator. This will initialize LCD 2 lines and 5:7 matrix. Then a call means absolute call for command write. Here this is command, and so we have to call the command write subroutine. This call command write subroutine. Then absolute call for delay. This will give LCD some time. After that, we will move 0E to accumulator. This will make the display on, cursor on. Now we will call absolute call for command write, a call for command write, call command subroutine. Then absolute call for delay. This will give some time to LCD. After that, we will move 01 to accumulator, move 01H to accumulator. This will clear display. Then absolute call for command write, call command subroutine. Then absolute call for delay, give time to LCD. After that, we will move 06 to accumulator. This will shift cursor to right. Then we again call absolute call for command write, as 06 is a command for LCD. So we will call command write subroutine. Then again a call, absolute call for delay, give time to LCD. Then we will move 84H to accumulator, cursor at line 1 position 4. Absolute call for command write, then we call command subroutine, then absolute call for delay, give time to LCD. Now we have here move G to accumulator. G is our data. Now we have to call data write subroutine in place of command write. In place of G, we can use any data. Move G to accumulator, display G letter. Absolute call for data write. Now we will call display subroutine. Then again absolute call for delay. This will give some time to LCD. Now move P to accumulator. This will display P letter. Then we will call, as P is data, absolute call data write subroutine. Then again absolute call for delay. This will give some time to LCD. Then we have to call, then we have move C to accumulator. Display C letter to accumulator. Now absolute call for data write, call display subroutine, then absolute call for delay, this will give time to LCD. Now we will move G to accumulator, this will display G. Again we call absolute call for data write and absolute call for delay, this will give some time to delay to LCD. Now this will display GPCG on the LCD display. Now we can change these characters, any character you require you can display on LCD screen. Now we have S jump, again stay here. Now command write subroutine, here send, we will move accumulator to port P1, this means send command to LCD, port 1 is connected to the LCD data bus. Now we will clear P2.0, it is connected to RS pin of the LCD, this will make RS 0 for command, means command register is selected. Now we will clear pin 2.1, that is read write equals to 0 for write. Now set bit P2.2, 2.2 is connected to enable pin, this makes E equals to 1. Then we will call absolute call for delay, as we have to make enable pin high and then low, high for some duration. So that duration is given by this delay subroutine. After that clear to make enable pin 0, then we will return. When data is supplied to data pins, a high to low pulse must be applied to this pin in order to latch in data present at the data pins for minimum for 450 nanoseconds. Then we have data write subroutine. Here we will move accumulator to port P1, after that we will set bit P2.0, means we have to select the data register, RS is made to 1, we will clear P2.1 as we have to write. So we will clear P2.1, that is read write pin, then we will set P2.2, that is we make enable high, after that we will call a delay, absolute call for delay, give time to LCD, then we will again clear P2.2, that is enable pin is cleared, enable pin is made 0, that is we make enable pin high to low, then we will return. Now move 52 R3 delay, then here too move 255 to R4, then here 1 decrement and jump till not 0, jump not 0 R4 here 1 and decrement jump not 0 R3 here 2, then return end. We can change the delay time by changing these numbers, that is 50 or 255. Now interfacing the keyboard to 8051 microcontroller. Interfacing the keyboard to 8051 microcontroller, the keyboard here we are interfacing is a matrix keyboard. The rows and columns are connected to the microcontroller through ports of the microcontroller 8051. We normally use 8:8 matrix keyboard. So, only two ports of 8051 can be easily connected to the rows and columns of the keyboard. When a key is pressed, a row and a column make a contact. Otherwise, there is no connection between rows and columns. Here this is the interfacing diagram of 8051 with 4:4 keyboard. 4:4 means this keyboard has 4 rows and 4 columns. That is, it is hex keyboard. Here we have used two ports of 8051, that is port 1 and port 2. Port 2 is the input port and is connected to the columns of the keyboard, and they are made high by connecting it to VCC, and port 1 is made output port, and by our program we can ground these rows. Now, this is a flow chart for keyboard interfacing. First of all, start, then ground all rows. After that, we will move to this point, read all columns. Is any key down? No. Go back and then read all columns again. If yes, then wait for debounce. Debounce means when a key is pressed, it takes some time to come its position back. That time period is called debounce time. Then read all columns. Is any key down? If yes, go ahead. Otherwise, go back. If no. If yes, then ground next row. Means we will ground first row, then next read all columns. ठीक है? Key press, next, is key press in this row? Yes. Find which key is pressed. If answer is yes, if any key is pressed, then find which key is pressed. If no key is pressed to this row, then go back and ground the next row and check, is any key pressed. If key is pressed, find which key is pressed and get scan code from the table and return. Scanning and identifying the key. 4:4 matrix connected to two ports. The rows are connected to an output port and the columns are connected to an input port. If no key has been pressed, reading the input port will yield ones for all columns, since they are connected to VCC, that is they all are connected to high, that is VCC. If all the rows are grounded and a key is pressed, one of the column will have 0, since the key pressed provide the path to ground. It is the function of microcontroller to scan the keyboard continuously to detect and identify the key pressed. Grounding rows and reading the columns. To detect the pressed key, the microcontroller grounds all rows by providing zeros to the output latch. Then it reads the columns. If the data read from the column is D3 to D0, that is all ones, no key has been pressed, and the process continues until a key press is detected. However, if one of the column bit has 0, this means that the key press occurred. For example, if D3 to D0 becomes 1101, this means that the key in the D1 column has been pressed, that is D1. This column is D0, D1, D2, D3. After a key press is detected, the microcontroller will go through the process of identifying the key, starting with the top row. The microcontroller grounds it by providing a low to row D0, only then it reads the column. If the data reads is all ones, no key in that row is activated and the process is moved to next row. It grounds the next row, reads the columns and checks for any 0. This process continues until the row is identified. After identification of the row in which the key has been pressed, the next task is to find out which column the pressed key belongs to. Upon finding the 0, it pulls out the American Standard Code information interchange code for that key from the lookup table. Now we have interfacing 7-segment displays. LED displays are more power hungry, more pin hungry, that is 8 pins per 7-segment display, but they are cheaper than LCD display. So, LED 7-segment displays are very commonly used numeric display. LED displays are preferred when there is no constraint of power consumption. A 7-segment display contains 7 segments arranged as an 8 with 1 common lead and 7 individual leads for each segment. If all the 7 LEDs have common anode, then it is called common anode 7-segment display. If all of them have common cathode, they are called common cathode 7-segment display. By turning on these 7 segments in various combinations, numbers from 0 to 9 and some alphabet characters can be displayed. This is a 7-segment display. Here are the 7 segments and 8th segment is for decimal point. This is the 8th segment. Now, the 7 segments are from A, B, C, D, E, F, G. By turning on any, as example, if we want to display 1, we have to turn on B and C segments and so on. Normally, a 7-segment display also has one more segment for display of a period, that is full stop, which is labeled H. If 7 segment A, B, C, D, E, F and G of the display are directly connected to port pin Px.0, Px.1 to Px.6 respectively, then to display an hexadecimal digit, hex codes can be used from the table. These are the hex codes. These are the hex codes for common anode type configuration and these are the common cathode type configuration. To display 0, suppose we have a common anode, we have to send C0. For common cathode, we have to send 3F. Now, if more than one display is to be used, then they are time multiplexed, taking the advantage of persistence of vision. The human eye cannot detect the blinking if each display is turned on every 10 millisecond. The 10 millisecond is divided by the number of displays used to find the interval between updating each display. Common anode display are most suitable for interfacing with 8051. Since 8051 port pins can sink current better than sourcing it. Here is the interfacing of single common anode display to 8051. In this case, 7 segments, that is A to G, are connected to the port 1 pins, and decimal point is also connected. Here only one port is required for single display. If we have more displays, in this example we have 4 common anode displays, 7 segment displays. In this case, 2 ports are used.